2, 1.
Mhm.
Good morning, good afternoon, or good evening, depending on where you are tuning in from today. And thank you for joining this TechStrong learning experience with Gremlin. My name is Tip, and I'd like to welcome you to our TechStrong learning program. This session will be available afterward on demand. We will also be sending you a link to the recording after we conclude. Please send any questions that you have to the Q&A panel on the right side of your screen, and join us in the chat by telling us from where you're tuning in from. Share your experiences, your comments, your understanding of the matter. We want to hear it all from you and engage with you. Any questions that we're not able to get to, we will follow up with you shortly after the program concludes. We also have handouts available for downloading in the resources section on the left side. Let's kick off today's topic, improving resilience for GenAI workloads on AWS. Thank you everyone for joining us today. We have Andre Newman, Shivam Patel, and Dylan Suvaj with us today. Andre, can you take it from here?
Definitely. Thank you, Tip. Hey, everyone, and welcome to today's webinar. Quick introductions about who we are. My name is Andre Newman. I'm a Senior Reliability Specialist at Gremlin. I'm joined by Dylan Suvaj and Shivam Patel, Partner Solutions Architects at AWS. During this presentation, Dylan and Shivam are going to talk about a bit about the different architectures that people are using for GenAI on AWS and what reliability looks like in them. And then I'll be wrapping us up with a demo on how this works in practice in Gremlin. And then, like Tip mentioned, we'll be ending with Q&A. So if you came with questions, feel free to enter them in the Q&A panel. And if you think of them as the webinar goes on, also feel free to enter them, and we will get to them later. So again, quick look at our agenda today. I'll start off with the introduction to resilience testing, a quick overview, what it means, how it works. Dylan, Shivam, and I are going to walk through some example architectures of how folks are using AI in AWS, including LLM Kubernetes-based architecture, Q&A customer service bots, and also intelligent document or RAG processing. Again, I'll end with a demo about how to actually test this using a reliability testing tool, Gremlin, and then we'll wrap up with Q&A. So to jump right into it, it's helpful to have some context around what resilience testing is exactly. Resilience testing is built on a process called fault injection, where we simulate failures on systems in order to test their reliability holistically. If you haven't heard of it before, fault injection is exactly what it sounds like. We're intentionally creating faults and failures in a system and seeing how it reacts. This can be anything from consuming excess CPU to testing scalability, or even dropping network traffic to simulate a zone or region outage. Of course, we don't recommend people just go around stressing out their system. We recommend taking a more measured approach. So with a customer base, we typically see two main methods. First is chaos engineering, which is one-off exploratory experiments. This is meant to help find unknown failure modes in your system, things that you're not expecting or that you weren't aware of. And then there's validation testing, which is sort of taking this chaos engineering practice and standardizing it and scheduling it so that it runs regularly. This lets you track reliability over time, verify resilience to common problems, and uncover regressions so they don't come back later to cause an incident or an outage. And actually, a quick anecdote about this. One of our customers had a Redis database set up as a cache. And the idea behind it was that if the cache was unreachable, their system would fail over to the primary database, essentially bypassing it. And on the surface, this is a pretty standard, uncomplicated setup, but it's still good to check just to make sure that you can actually do it. So they ran a quick test that introduced a bit of latency between the Redis database and their application, and it immediately browned out. And it turns out that the time before the failover was set to be longer than the timeout time, so the failover never triggered. This is a great example of chaos engineering or exploratory testing. They created an experiment to test a hypothesis they had about their system. It didn't behave the way they were or expected, so they ended up uncovering this as a weakness, and by fixing it, made their entire application more resilient. But now, the good thing is that they can take that and apply it to everywhere else in the system where they use caching. So by fixing this issue once, you can end up fixing it a bunch of different times, depending on how big or how complex your architecture is. And that's where you have a use case for validation testing. You're taking this exploratory test and then, for lack of a better word, processifying it so that you're doing it over and over again, and you're able to catch that before it becomes an issue in the future. So the question now is, how do you apply these testing concepts to AI? Or I guess to put it more generally, where should you look to make reliability improvements in AI deployments? So there's a few places that we recommend looking. First is being able to route distributed AI systems around failures, right? AI and LLMs especially are these big distributed applications that are running across hundreds or even thousands of nodes. They're sending traffic over networks all the time. So what happens if some of those networks fail or if some of those interconnections fail? Well, you can use chaos engineering to simulate these failed networks and nodes in order to retest, or rather, to test your application's rerouting abilities. On a similar vein, if dependencies are unavailable, you need to be able to fail over if that's the case. So if you're communicating with an external RAG or some other document database, and that becomes unavailable, what's going to happen to your AI model or your AI application? Is it going to detect that failure and fail over to an alternative? Is it going to return an error message to the user? Is it just going to time out? You don't really know until you take that chaos engineering tool and simulate those services going offline and those dependencies going offline, and then observing your application. Very popular and very topical to AI is GPUs. We rely on a whole bunch of them and their power in order to make these models run. So we need to make sure that they can function under heavy load. Well, tools like Gremlin can actually stress out GPUs and make them run as if they were running a really intensive model. This is helpful for testing scalability and making sure that having a GPU that's heavy stressed out and under heavy load isn't going to take down your entire system or make your entire system unresponsive. On a similar vein, we have to be able to scale up and down, right? It's very common in distributed systems, not just AI, but the weight of these AI models and how big they are just makes this even more relevant and more of a requirement. So we can use tools like Gremlin to scale our systems by ingesting CPU or consuming RAM and making sure that we can trigger auto scaling thresholds so that our resources can scale up and down dynamically. And last but not least, there's ensuring data integrity and accessibility. And this is, again, comes down to network interconnections and making sure that your systems can send data back and forth reliably, even if the infrastructure that they're working on isn't quite reliable. So again, this is using network-based experiments and chaos engineering tests to test those connections and make sure that your model retains its integrity, even when the systems are being stressed out, when resources are being consumed, and when network conditions are unfavorable. So now I'm going to hand it over to Dylan, who's going to walk us through some of these example architectures that folks are running on AWS.
Yeah, thanks, Andre. Appreciate it. A bit about me, I'm PSA at AWS, been here for about 3.5 years. I work with ISVs predominantly in startups, and happy to be here today. So yeah, up to now, we've discussed challenges of running large language model workloads, generative AI workloads, how they differ from traditional applications, key failure scenarios we need to account for. But now I want to look at more of a typical Kubernetes resilience architecture, discuss a little bit about how we architect these applications at AWS, and discuss structure to keep those large language model workloads running reliably. And we have to actually test how they work. So to start, we're going to break down the architecture. So what we're looking at here is a Kubernetes-based LLM, or large language model inference system, running on Amazon's Elastic Kubernetes Service, or EKS. If you're not familiar with EKS, it's AWS's managed Kubernetes service. So automating deployment, scaling, maintenance of containerized applications based on Kubernetes. This architecture is designed to handle high demand AI workloads, but maintain that scalable and resiliency while providing the most control and customization behind it. So first, we have an application load balancer. This is the first entry point for requests. It routes traffic to the instances that are running large language models inside Kubernetes. So if this fails, users can't reach the model at all. We also have a horizontal pod autoscaler, or an HPA. Since LLMs are compute heavy, we use the HPA to dynamically scale inference pods. So if the HPA is misconfigured or too slow to react, we can either over provision and waste money, or under provision and cause timeouts. We also have the EKS control plane. This is where the Kubernetes orchestration happens, scheduling workloads, managing cluster health, ensuring availability. If the control plane is overwhelmed or probably more likely misconfigured, new pods might not start up at all. We also have the NAT gateway. So this component allows for internal Kubernetes workloads to communicate externally, for example, to third-party data sources or web pages, et cetera, or to other applications over the internet. If this fails, any dependency that relies on that API call will break. So, what can go wrong, right? Now, just because we have this architecture doesn't mean it's failure-proof. Maybe we've even set up resiliency in the design, right? But let's talk about the 3 key areas where we want to actually test the resilience to ensure it actually holds up under real-world conditions, right? Because planning and testing often are different. So, right, we want to ensure scalability. LLM inference can be extremely intensive, requiring rapid scaling. If the pods can't spin up fast enough, requests could start queuing, failing, right? So I want to start with a quick question over to Shivam. Shivam, what are AWS best practices for making sure those LLM workloads scale quickly and efficiently, and how would that differ from a typical workload?
Yeah, for sure. Let's talk a little bit about why LLM workloads differ from a typical workload. The first key difference is going to be the model loading overhead. So scaling LLMs involves delays due to loading the large model weights into the GPU memory, and that's much different from a typical workload, which might have much shorter delays and lower latencies, opening up or spinning up another pod. The second is, in typical workloads, you may track metrics such as CPU. With an LLM workload, you'll need to configure your cluster to track GPU metrics, or you may even opt to track custom metrics such as the amount of requests in the queue. So for example, if you have an influx of customers using your application, lots of requests coming into your LLM, it'll take time for those processes to run through, and you may opt to track that. For example, you may want to reduce that delay that your end customer experiences when receiving a response. So you opt to use that custom metric. And so some of the best practices is, one, before we even think about scaling and configurations within the cluster, ensure that you're well below your throttling limits. LLM workloads on AWS will have some soft limit. You can request for that limit to be increased, but you may not need to. Just double check that you're within those limits. And the second is that make sure you have enough GPU capacity associated with your account. Again, soft limit, you can request for it to be increased if needed. And then in addition to that, we also recommend ensuring that you're using an LLM model which fits the bill of what you need. What I mean by that is, if there's an opportunity to decrease the size of the model and still meet the response that you're looking for, you may not need the most complex one. This will ensure that when you spin up pods, they'll spin up faster, because typically less complex models are small. Save costs in this aspect as well.
Awesome. Thanks for that, Shivam. So that being said, Andre, how do we actually test scalability to make sure the various auto scaling Shivam was mentioning responds fast enough under load? Does Gremlin provide functionality that can help us with this?
Yeah, so this is actually one of the most common use cases with Gremlin. We have a whole category of experiment types called resource experiments that are designed specifically to do things like simulate high CPU load, simulate high memory usage, and even high GPU usage. So the way you would approach this is you would have your auto-scaling rules set up in AWS the way you would think that they would work. You would run one of these resource tests using Gremlin to actually trigger those auto-scaling thresholds and make sure, of course, that your systems can not only scale up as you would expect them to once they hit those thresholds, but once they're done scaling up and once the systems or resources return back to their normal levels, that you can scale back down. So it's kind of a two-way test just to make sure that not only are you creating the capacity when you need it and that you're getting it quickly, but also that you're not over provisioning when you don't have the demand that's necessary to have those resources. So again, you can do this for CPU, memory, GPU, even disk I/O and disk capacity. Like Shivan mentioned, whatever metrics you use to track the performance or capacity of your workloads, you can use those and just simulate high usage on those and make sure that you're able to scale effectively.
Awesome, thanks. So on to the next of the 3, right, for this first architecture. The second one was going to be detecting Kubernetes misconfigurations, right? Kubernetes is powerful, can also be complex. Misconfigurations are, the most common, probably one of the most common causes of outages. Incorrect resource limits, pod scheduling issues, small mistakes can bring down the system, right? So Andre, from a resilience testing perspective, how do we proactively catch Kubernetes misconfigurations before they cause downtime?
Yeah, so this is actually a big feature we released last year called detected risks. I've talked a lot about sort of testing that you do actively, but in this case, detected risks are a lot more passive. What they are they're predefined risks that we look for in your systems. So, for example, we look for things like pods that are in a crash loop back off state, pods that are in a image pull back off state, ones that don't have liveness probes or tests like those configured. Very common, very generic to all different workloads, but still really important to have. So as soon as you add your service into Gremlin, you can go into detected risks and see which ones Gremlin has automatically detected, and based off of that, be able to take actions to mitigate those risks and resolve them. And then if you want to take a more active approach, go back and actually run those reliability tests to make sure that you're mitigated those risks.
Cool, awesome. So Shivam, how does Amazon EKS help you, with setting up those operations so that they're resilient in the first place, right? What does Amazon EKS do for you compared to like running in Kubernetes on, like, for example, EC2 or on-prem?
Yeah, there's a number of benefits of running on Amazon EKS versus trying to build it from the ground up on EC2. A big example is Amazon EKS provides the orchestration capabilities through its managed control plane, and by default, it's actually deployed to multiple AZs for high availability. In addition to that, when it comes to like auto scaling, we previously spoke about it. Amazon EKS supports Carpenter and Cluster Autoscaler. So those are quick ways to incorporate that into your cluster. Another benefit is once EKS is all hosted, you can keep all your GenAI traffic within the AWS intranet. And so that's a benefit that you don't need to call out to the internet to make an LLM call. And finally, there's a huge community behind Amazon EKS. There's numerous public resources. Some of them are actually linked in the handout section of this on how to deploy LLM workloads on EKS. And that's in addition to the strong open source community of Kubernetes folks. And so that's just a strong foundation to get started on deploying LLMs to Kubernetes.
Awesome. Thanks for that. So the last point I want to talk about in this architecture is really the validation of resilience to network failures. The application is not very useful if it can't connect to the databases and other applications that rely on it, right? LM is not going to be useful in that sense. Any disruption in the network traffic, whether at the ALB, NAT gateway, or external API level, will cause cascading failures. So Shivam, how does AWS recommend designing large language model applications to minimize disruptions, enable failover?
Yeah, for sure. I previously just spoke about the Kubernetes cluster is automatically deployed to multiple AZs by default. So in that aspect, you're checked off. But remember, that's within one region. So when it comes to failover, we recommend implementing a DR strategy. And the most basic one would allow failover to another AWS region. In such a case, you would deploy a primary and secondary EKS cluster to two different regions. The secondary region does not need to be a hot standby. You can always opt for a more cost-effective strategy like using cross-region replication of your EKS cluster in the event of a disaster. And so in this case, you would ensure that you have ongoing automated backups of your cluster, and then in the event of a disaster, it replicates in the secondary region. Now, within an AZ and scaling of pods, I would revert to our initial discussion where we spoke about how to scale out LLM workloads to scale effectively. So that takes care of your resiliency within the region. And then beyond all that, you should always review your network topology and ensure it's fault tolerant. So for example, if we take a look at this architecture, the AWS ALB is fault tolerant. It's deployed to multiple AZs by default. However, a NAT gateway must be manually deployed to multiple AZs. By default, it's actually only deployed to a single AZ. So keep that in mind when you're setting up your DR strategy.
Awesome, thanks for that. Yeah, good call out on the NAT gateway there. So found takeaway for this architecture, we've built a scalable Kubernetes architecture. That doesn't mean it's resilient by default. We can plan, right? But we need to actively test for failures, misconfigurations, and scaling issues before they cause real prod outages. So I want to transition over to the next architecture. This is going to be a Q&A chatbot. So we've just talked about how to ensure resilience for those LM inference workloads that are running on Kubernetes. Now I want to talk about a different but equally critical and maybe the most common AI use case, Q&A chatbots, customer service AIs. So the previous architecture focused on large language model scalability, GPU-heavy workloads, compute-heavy workloads. This one's more service-oriented, relying on AWS managed services, serverless components, database integrations. So that means our biggest risks here aren't just compute failures. They're more about data access, service redundancy, application-level resilience. So let's walk through about what can go wrong here. And again, how can we test for resilience before those outages happens? So to break down the Q&A chatbot, this architecture supports a real-time Q&A customer service bot. Again, those are all going to be in the handout sections for deeper dives in the architectures. They're all built on AWS managed services. So this includes the data access layer. The chatbot pulls from sources like Amazon DynamoDB, OpenSearch, S3. If any of these fail, the chatbot might give incomplete or potentially worse, incorrect responses. Serverless processing, right? Lambda functions handle much of the business logic or integration, connecting user queries to storage, AI responses. If a function times out, fails to execute, the entire system can become unresponsive. Service redundancy and API gateway, right? Amazon Incognito manages authentication, API gateway routes requests. Service like Amazon Lex, power conversational AI. If one of these fails or gets overloaded, misconfigured, can the bot degrade gracefully? Right, I can already look at the architecture and suggest that it would probably be valuable if we had some sort of messaging system using Amazon SNS or SQS for pub sub, right? So now let's talk about how we test for resilience in this system. Everything, because they're manages, right? They're all managed services. We assume that they will always be available, but it's a dangerous bet. Our Amazon CTO, Werner Vogels, famously always says everything fails all the time. So at AWS, we always design our applications and our systems to be designed to be resilient to failure, even in the context of managed services. So number one, we want to ensure access to data. Data is the backbone of the chatbot. Without it, responses would be incomplete, inaccurate, or fail entirely. Even if the bot functions with partial data access, missing context could lead to incorrect answers or, again, worse, right, hallucinations and a poor customer experience. So how do we test for resilience? Things like network and data resource tests, simulating database latency spikes. What happens if DynamoDB OpenSearch queries slow down? Network outages, storage issues, right? Does the chatbot fail over to cached responses? Does it break entirely? So Shivam, what are AWS best practices for ensuring high availability data access in a setup like this? You're on mute, Shivam. Yep.
Yeah, data is really important when it comes to generative AI applications. And because of the number of systems involved in terms of data, speaking about each of them is the most important. So in this case, we have S3, DynamoDB, and OpenSearch. Services like DynamoDB and S3 will provide high availability. Things like S3 right out of the box provides 99.99% availability over a given year. And DynamoDB is also deployed across multiple AZs within a region. You can increase the availability of DynamoDB by using things like DynamoDB global tables, which will sync your data across AWS regions for additional availability. And then when it comes to services like Amazon OpenSearch, RDS, or even running your own database on EC2, you have to ensure that you have a multi-AZ deployment. So in this case, it's not managed for you. And that's where you need to really review and ensure that you're meeting your high availability goal. Services such as Amazon OpenSearch or RDS will make this process simple for you by providing configuration options right in the AWS console or CLI. If we take a look at this architecture, we've opted to use Amazon OpenSearch. Within the console, OpenSearch has an easy create process for a cluster deployment across multiple AZs with a standby, and it only takes a few clicks. And then with all databases, we always recommend to have an automated, ongoing, scheduled backup.
Awesome. Thanks for that, Shivam. So again, following a similar theme as the previous architecture, Andre, how do we actually test these failures at scale without breaking the system?
Yeah, so kind of like I mentioned before, we have a category of resource experiments. In this case, we have a different category of of experiments called network experiments. And just like the name implies, these are useful for testing various network conditions like a complete blackout. What happens if you lose connection to a dependency? You can inject latency as well, or even packet loss. So what if the network is degraded? Kind of like Dylan was mentioning earlier, AWS's services are mostly managed. So unfortunately, you can't just go into AWS's systems and start causing things like slowdowns. They'd get really upset, and also that's not possible. So instead, what you can do is focus on your own application's connection to these other systems that you depend on. So what happens if your application or your front end loses connection to S3 or DynamoDB or Cognito or whatever it might be? How does your system respond to that? How does it react to that? Does it show an error message? Does it just not respond to the user's requests at all? These are things that you can proactively test using these network experiments. And again, making sure that your applications can fail over reliably, that if you use backup services, that they can fall over to those. And if none of that's possible, making sure that they can degrade gracefully and without, completely damaging or the user experience.
Awesome, cool. So on that note, right? So redundancy of managed services and pennies are important. So even if the chatbot can access the data, if it's relying on multiple managed services like Lex for natural language processing, Poly for text-to-speech, Bedrock for generative AI, if any of these are unavailable for whatever reason, we need a backup plan. API gateways unreachable or Lex becomes unavailable. Do we have fallback mechanisms? What happens actually if a region occurs, right? How do we actually test that? Simulate service unavailability. How do you test an AWS managed service if it's suddenly unreachable, as you mentioned? Multi-region failover testing. Are they deployed redundantly, right? So, Andre, how do you actually test redundancy actually working before a real failure happens?
Yeah, so one of our experiments, we actually call it the black hole experiment. The idea behind that is it simulates a complete network outage, but you also have full control over how that outage occurs. So we let you determine which host names are impacted, which IP addresses, which ports, if you want to block a specific service and not necessarily to a specific destination. And you also are able to control how long that blackout lasts for. So what you can do in this case is you can choose any one of these services based off of its host name or port number, if it has a dedicated port or anything like that. Even targeting specific availability zones or regions, because we're able to detect metadata like that from services deployed on AWS, we're able to see things like EC2 instance names, regions where they're deployed, VPCs even. So you can go in, fine tune your parameters, pick that exact connection between your service and between the database or Lex or whatever it might be, and then run that experiment and observe what happens to your application, right? See how it responds. The ideal would that be it can fail over to a backup service, but if it can't, or if it doesn't work the way you expect it to, then you're able to find that just by running these experiments too.
Cool. So the last point of this architecture I want to talk about is really that serverless application level error handling. The system relies heavily on AWS Lambda. So we have to make sure that application level failures like the timeouts, cold starts that I mentioned earlier, don't crash the whole system. So Lambda has execution limits, concurrency, potentially concurrency constraints, cold start delays. If one function fails, will the system retry correctly, or does it just time out? So how do we actually test for resilience, right? Andre, what's the best way to test serverless failure scenarios to make sure the chatbot doesn't just break? How do you test Lambda failures?
Yeah, so this is a different feature that's available in Gremlin called failure flags. And a lot of what I talked about previously has had to do with infrastructure level failures. So we're talking about network experiments on specific network devices. What happens if you need to get more into the application level, into the code level? That's really where failure flags comes in. And part of it we designed specifically for AWS Lambda, because in Lambda, you don't have access to a node or a cluster or any of those concepts. You're just deploying code and AWS takes care of the rest of it for you. So with failure flags, you have a bit more control and customization over the type of experiments you want to run. But again, we also give you a couple of defaults, latency and exceptions. So in this case, you can go into your Lambda function, run an experiment that adds latency to each of your network calls to a dependency. That helps you test for things like timeouts and also for errors. And as well, being able to simulate API response failures with exceptions. So you can take a response back or a request to a specific service, simulate a failure by generating and throwing an exception or causing an error. and seeing how your application handles that. So again, failure flags is really useful for getting down there into the code level and making sure that everything works the way you expect it to.
Yeah, that's powerful. Awesome. Thanks for that, Andre. So I want to transition to our last architecture, the document analysis. This is another very common use case. We've covered LM inference workloads on Kubernetes, Q&A customer service chatbots. The last architecture here, document analysis AI, is going to be unlike chatbots, which respond to user queries in real time. This is for processing documents, extracting information, enriching content, right? Depending on the use case, it could be running quietly in the background, or it could be actually handling high stakes workloads like processing financial applications, insurance claims that require real-time speed and accuracy, right? It could be batch, could be real time. So the resilience challenges here aren't just about availability. They're about ensuring consistent processing, predictable scaling, system observability. All right, so to break down the document analysis architecture, let's talk about how it's designed. Firstly, we have the storage and data ingestion side. Everything starts with Amazon S3. Documents are uploaded here before processing. If the system can't retrieve the files, nothing else works. AI processing enrichment, right? We have the managed AI models handling text extraction like Amazon TextRack, entity recognition, summarization, enrichment with Amazon Bedrock. Failures in the AI processing can waste compute resources, again, delay business critical tasks, depending on the workload. We also have the Kubernetes deployment. Kubernetes is running the larger, more complex workflows to understand the writing and summarize it. These processes can take time depending on the length of the document and how complex you want writing analysis to be. Deploying to Kubernetes allows you to scale out the process when a large amount of documents need to be analyzed, or open up the door to make use of those really large language models, have more control. We also have the serverless compute again, serverless Lambda functions. Again, we want to test application level failures again, right? A lot of those integrations come from Lambda. So let's talk about how we test resilience in the system, right? We covered some of the infrastructure testing in the previous sections. So here I want to focus on the GenAI specific risks, operational challenges, right? The first one's going to be AI scalability and human review bottlenecks. One of the biggest challenges with AI document analysis is that it's often tied to human review workflows. You can scale AI models quickly, right? But you can't scale humans indefinitely. So how do we handle that bottleneck? Shivam, when designing those GenAI workflows that involve, human verification or human in the loop, what are the best ways to manage scaling constraints?
One of the most important steps in implementing a screening mechanism with the human workforce is reducing the number of cases that require the human intervention or review. So this allows that team to focus on high-risk cases. And the importance of this is actually amplified when you have a large scale-out event. Because you can imagine if there's a huge influx of documents or requests, now there might be a higher number of high-risk cases. And so depending on your application, there's a number of methods you could use. The most obvious one is reducing the number of processed documents or inferences in the case of high-risk applications. So what that might look like is identifying which workloads or which documents need to be processed now versus some that can be processed later on when the queue is a lot shorter. The other one is variably changing the threshold for what you quantify as a high risk. That level of change I would only recommend in a low risk application. And what I mean by a low risk application is there isn't a business impact if that threshold is changed and an error gets through. The last one is if your application has something that's quantifiable, there's numerics used, for example, extracting numbers from a PDF, then implementing a logical checksum can be a way to have a review done. So let's say there's like a mortgage application coming in, a lot of numbers on a PDF, and there's generative AI being used to scan that PDF and pull those numbers. You can run some level of arithmetic to figure out did the scanned numbers make sense when I run this equation? And that's a great way to check as well. And then a very important thing I want to mention when it comes to human workforces and generative AI is to always run a game day. A game day is when you'll simulate a fault, some type of failure or a scale out event, and then actually have the teams pretend like this is occurring and seeing how they behave. You want to ensure that any of the mechanisms, both on the operations side and from the infrastructure side, will work in a real life scenario.
Cool. Thanks for that, Shivam. So that being said, with so many moving parts, AI models, storage, serverless Kubernetes, you need a strong observability stack to detect and respond to failures fast, right? So failures in AI processing aren't always binary. The system might not fully crash, but it could degrade, slow down, or return incomplete, or again, even worse, hallucinated results. Without good observability, you might not even notice. One of the best ways to validate observability is by injecting failures on purpose. So if you drop an AI service or slow down a storage dependency, how does your team detect and respond quickly? So Shivam, how does AWS help teams with observability instance responses in AI workloads?
Yeah, a lot of our services have built-in logging, and all these logs get sent to CloudWatch logs. So in the case of Bedrock, for example, you'll have things tracked such as invocations, response streams, runtime metrics, input and output tokens. And that's one avenue that you can check for the observability of your generative AI services. The second is that we have tools like AWS X-Ray, which allow AWS developers to analyze and debug microservice architectures. You can trace requests end to end through multiple services, like let's say Lambda calling Bedrock, Bedrock pushing that response to some other service. These tools are also very important in identifying latency issues. And the reason why we keep bringing up latency is because when it comes to AI workloads, a really poor customer experience is waiting for a response to be generated or a delay occurring in something being processed. And so low latency leads to better customer experiences. And then another thing to mention that's quite important that's specific to GenAI is hallucinations, incomplete responses, and then the latency concerns again. And so services such as Bedrock will have features built in to prevent these things. Bedrock guardrails, for example, can be configured to add additional safeguards to reduce hallucinations and prevent responses from speaking about hot topics. And hot topics can be anything that you request it to avoid. There's also tools within Bedrock that prevent responses from being sent out unless they're complete. So it waits for a complete response to be generated and then sends the response out. There's also abilities within Bedrock to only respond if the response contains material from your company's knowledge base. That way, it's not trying to create a response from thin air or from its training material. It's only pulling referable data from the database or knowledge base that you point to. It's also important that although there's all these configurations and all these tools, they still need to be tested. And that's really where Gremlin comes in to be able to make sure that your configurations are set. It's one thing to put into Bedrock X number of configurations to prevent hallucinations, and it's another thing to have it all tested.
Yeah, I'll actually second Shivan's point on the importance of observability, because even at Gremlin, we also rely on observability too. Right? We have this saying that you don't know how your systems are behaving until you're able to actually see into them. And that's really where observability tools like CloudWatch come in. It also doubles for experiments as well. So while you're running an experiment, Gremlin will actually use our observability tool in the background to monitor your systems to make sure that they're still performing well. And while these can be anything that you want to choose, they can be metrics, they can be alerts, they could even be just pointing directly to your website's front end or URL. But we also have what we call intelligent health checks, which are direct integrations into AWS to be able to monitor CloudWatch metrics for you. So let's say you have your service set up in AWS and you have an ELB, a load balancer that's pointing to it. Gremlin can take those load balancers metrics and create metrics around that based off of historical data. And using that, be able to infer whether the target service is available, unavailable, healthy, or unhealthy, and use that to determine the success of a test. So I'll show you how that works in practice during the demo, but just went into second Shivan's point that observability is super important when you're dealing with complex workloads like these.
Yeah, thanks for that, Andre and Shivam. So the last piece I want to talk about before we wrap up and move over to the demo is safe and controlled failure testing, right? A big concern with testing AI systems is they could be costly to run depending, both in production and staging environments. If you have a lot of, for example, GPUs spun up, right? So this leads to a difficult trade-off. Do you test in production, risk impact, or limit testing to staging and risk missing real-world failures, which we all know will happen if you don't test them. So, start in pre-prod, but move to production testing when the confidence is high. AI testing in prod is inevitable because real-world data, scaling issues, and cost constraints often make staging unrealistic. So, Andre, how does Gremlin ensure safe, controlled failure testing in those production AI environments?
Yeah, so kind of like you said, we really recommend starting in pre-production, but like they say, prod is prod. You can't simulate it. People try, but you still can never get one-to-one parity. So eventually you really have to move in there. But we work with a lot of enterprises for who this idea is, really kind of concerning. So we make sure that Gremlin's built from the ground up with security in mind. So one of the ways that we support that is with immediate automatic rollback. So while you're running a test, we have these big red halt buttons where if you click on them, they send a signal to immediately stop the test and return your systems back to their normal operation. Same goes if we detect a failure on our side. So let's say the Gremlin agent running on your system that actually orchestrates the experiments. If those lose connection to our SaaS platform, this will immediately trigger a switch to have them end their experiments and return your systems back to normal. Just because we want to make sure that you're not consuming CPU indefinitely just because you lost connection to Gremlin's backend services. And this is also, this cascade. So if you have multiple experiments queued, that queue will essentially be erased from the agent side and won't be restarted until it regains connection and you go back in and restart them manually. So again, we try to offer as much safety as possible while you're running these experiments in production because we get it. It's scary, it's risky, but we try to mitigate that risk as much as possible so you're just getting the results that you want to get.
Thanks for that, Andre. So to sum it up, AWS provides the infrastructure to run those AI workloads, the observability tools, and a wide range of services to both let you have complete control or offload some of the undifferentiated heavy lifting to AWS. Gremlin, helps you validate that they work under failure conditions, right? Help prevent those failures in the first place and prove that that's true by testing it. So, Andre, maybe I can pass it back over to you now for the demo. We can go deeper into that.
Awesome. Yeah, for sure. So I've actually got my environment already set up in the background. Just to give you guys a bit of context on what this is, I have a couple of services running on Kubernetes. One is Anything LLM, which is a front end to a bunch of different LLM services. And in the background, I have Ollama running, which is actually running my AI models. If you remember from earlier in the presentation, this is that first architecture we saw of the Kubernetes LLM. But basically, what I'm going to show you is how we can track this deployment using Gremlin, how we can test the various services, how the tests impact our services, and being able to actually take that and make use of it and make this more of a recurring thing in your world. So like I mentioned, this is a basic LLM deployment made up of 2 services. I've got Anything LLM running. I can send a query through it. So for example, I have what are some ways to make EKS applications more resilient? It'll take a couple seconds while it talks out to Ollama, but the response should get processed pretty quickly. And that way I'll just know that my services are working together and that I'm able to get the response the way I expected to. I probably could have made this a little bit faster. Not gonna lie, this isn't a production application, but again, it's just here to show how this works in practice. But it seems like my Gremlin is taking a little bit longer than I expected to. All right, there we go. So we see it coming back. It's going pretty quickly. I'm using one of the GPU-enabled models on EKS. So the response when it starts coming back is actually pretty fast. So this just shows to me that my application is working and I'm getting the responses that I expected. So knowing this, let's take a look at how this works in Gremlin. So the very first thing I want to show you in Gremlin is actually going to be a report. This is called the team score report. This takes all of the reliability work that your entire engineering team is doing and shows it in one place. We have something that we call a reliability score, which I'll dive into in a second. But we also have each of our services here. And for each of our services, we have a list of tests that we've run on it. And again, a reliability score. So for each test, we can see whether it's passed or failed or whether it's even been run or not. And we also have what we call dependency tests, which for each of these services, if they talk to downstream dependencies. So for example, Anything LLM actually communicates with Ollama downstream. So you see I have these different dependency tests, these failure tests, this latency tests, and these certificate expiry tests. As you run each of those and you get those results, Gremlin determines using observability whether it passes or fails. And taking those results, it wraps those up into what we call the reliability score. And that's how you get these numbers here. These are wrapped up into the team reliability score, which you see up here. And then if you want to get that 30,000 foot view, it wraps up even further into a company level score, which you can see in a different report. But for now, let's actually take a look at one of these services. So I'm going to go to my services and let's take a look at Ollama. So I've ran a few tests in the past. They've come back with mixed results, partially because I'm really bad at configuring stuff in Kubernetes, but also just because there are some things here that are just part of the Ollama Kubernetes definition that can get worked on. That's not a dig at the Ollama team. They did great work, but again, there's some stuff that we can do to make this more resilient. But essentially, I've got my full list of reliability tests here. These are my resource scalability ones that we talked about a bit earlier. We also have some redundancy tests. These essentially shut down or terminate or stop one instance of the service. Since these are Kubernetes deployments, these will be pods. So for example, the host redundancy test will actually go in, terminate a pod, and then keep that observability check running, that health check running to make sure that your service can come back up quickly. And ideally that it will have replicas set that it can fall back to. But again, at the bottom, I have dependency test. Since Ollama doesn't have dependencies, there's nothing here. But if I were to check anything LLM, you would see those dependencies show up there along with their test results. So before I go and actually run in a test, I want to show you one more thing. I keep talking about health checks, but what exactly do those look like? So if I go into settings and then go to health checks, you have the option of either using intelligent health checks. These are the ones that we automatically create for AWS services, but you can also create your own health checks. These could be a number of different observability tools, or they can just be plain REST API or HTTP endpoint. So in this case, I'm going to actually go up here and enable intelligent health checks just by checking that box. Again, Gremlin uses the ELB that I had configured to actually go and create these health checks for me. I can use these with regular ones, but I'm just going to use these on their own. So I'll come down here, click remove, and now I have my health check set, and I can go start running experiments. So now let's go and actually start running an experiment. Let's pick the host test, right? I filled this one before. Maybe I've actually done some changes to mitigate this, so I can go back in and prove that it makes sure that it's still working. So all I had to do was go in, click run test. Gremlin automatically constructs a test. It pulls up the screen so you can keep track of how it's running. And in this case, this is actually an unexpected result, but an interesting one all the same. So we got this result back that it wasn't actually able to go in and run the test because it wasn't able to find the containers. If I wanted to learn more about why this happened, I can actually go into the experiment runtime and see that my containers aren't actually running. So again, you can come in, you can run experiments, and you can have unexpected results, but they still teach you more about how your systems are operating. In this case, I need to go back in and check my Ollama deployment, see maybe why my containers, or rather why my pods aren't deploying containers. Maybe one of them failed when I was running my query in the background. Maybe they're in the process of restarting and I just wasn't able to target them. But I don't want to leave you all empty-handed, so I'm actually going to go to anything LLM and run another test here and make sure that it can run okay. Just to show you what this looks like while a test is actively running. So again, Gremlin comes in, it starts up the CPU test, gets it going, and it uses our health checks in the background to monitor the service and make sure that it's still running okay. And while this test is running, I can even go back into my LLM and start sending it other messages like, tell me more about EKS resiliency. And now I'm using my application while the test is running in the background, just to make sure that in the case of the test, this is scalability. My application isn't impacted. I'm still getting the results back. Anything LLM still seems responsive and it's still streaming messages back to me. So even though we have the scalability test running in the background, it shows that this service is configured to actually scale correctly and that it can still handle user requests even while our CPU usage is high. So it's a good way to find issues, but also validate that existing issues work. And I know we're running a bit short on time, but I want to show you all one more thing, and that's detected risks. So earlier I mentioned Gremlin can go in and automatically detect certain configuration issues on your system. This is what that looks like. So on your service, you go to detected risks, and depending on the type of service you're running, you get this list of different risks that Gremlin looks for. Since I'm running on AWS and Kubernetes, I'll see a combination of Kubernetes risks here, as well as AWS-specific risks. And these are just automatically detected based off of my environment. So for each risk, there are two statuses. There's at risk, which means the service is vulnerable, and mitigated, which means it's not. And if a service is at risk and you're not quite sure what it means, you can just click on the detected risk and scroll down, and you'll get information about what it means, what it represents, why it's a risk, and even ways that you can fix it. And where possible, we also link back to original documentation. So a lot of these will link back to AWS's, in this case, it's the Kubernetes, so it links to Kubernetes docs. The original documentation, you can go straight to the source and understand what it means and how it works and how we're checking for it. So like in this case, load balancer AZ redundancy, cross-zone redundancy. Just click on the links and you're taking right to AWS's docs. All right, so before I jump back, we're just going to take one more look at our test to see how it's doing. And so far, our service is doing pretty good. Our health checks are coming back successful. Whoops. We haven't had any issues. I can double check on the status of my health check just to make sure that it's passed. And again, monitor the progress of my experiment in these experiment screens. So that was a quick 10-minute intro to Gremlin. I'm going to switch back to our presentation so we can start moving into Q&A and answering your questions. All right, so let's see if we have questions that have come into the Q&A panel. Okay, so we have one that might be good for Shivam. How do you see people deciding between managed or unmanaged services for AI on AWS?
Yeah, it really comes down to the use case that you have in front of you. Things like size, how knowledgeable you are on the AI services, how much, like, is this a POC or a full production rollout, or how early you are in your AI journey will dictate where you should lie between unmanaged and managed. If it's a quick POC, you're early in your AI journey, you want to test out what it might look like, we usually lean towards a managed service because it'll be easier to get started. A lot of the infrastructure is taken care of for you, and you can do a quick test, spin it up and spin it down. For an unmanaged service, things like deploying to EC2, Kubernetes, or getting really deep dive into SageMaker, we recommend that you have a good understanding of AI. You might be working on something a bit more complex that requires more custom configurations, or it may be a full production rollout, which has large scale to it, where you would benefit from an unmanaged rollout of this service.
Yeah, I just want to add a little bit to that, Shivam. I think it's important to think about the time to value here. The time to value in a business context will likely be higher often with managed services, right? We want to really prioritize that. We're not, we don't want to focus on doing, the heavy lifting involved with the infrastructure, right, maintenance. We want to offload that to AWS so we can get value quicker, right? So that's why we typically would start with thinking about using managed services.
Cool. And one thing I'll add to that is that for managed services, the benefit of that is you really are able to kind of like Dylan said, your time to value is a bit shorter, so you can just hop in and start running your applications. One other thing to consider about unmanaged services is that for things like running applications on EKS or EC2, you're able to leverage AWS's native reliability for their system uptime, but for things like application and workload reliability, that really falls on you. So it's up to you to really run those reliability tests to make sure that your services can withstand those different failure modes. The nice thing is that you get a lot more control over exactly how those run, but again, you really want to be on top of your reliability and make sure that your applications and your workloads are taking full advantage of that AWS infrastructure reliability. So we had another question come in. I remember Palantir Foundry has similar health check and resilience for model capabilities. Are they using similar tools like yours? To be quite honest, I don't know a whole lot about Palantir Foundry. I'm assuming they're like a cloud platform or something similar, or AI hosting platform. Realistically, it depends on what they use for internal health checks. So if they're using their own health checks to make sure that their models are up and resilient, then yeah, it would be very similar. The thing about Gremlin is that we cover a much broader range of resilience testing. So while you can use it for AI, you can also use it for other workloads. We focus a lot on distributed network workloads, but honestly, any workload that you're trying to run in a production environment or that you're using to serve customers, you can test using Gremlin. So most likely the actual operation is similar, but we have a very broad spectrum of applications and workload types that we test for. Cool. Do we have any more questions that came in? All right. Well, if not, I think we can wrap it up. I can hand it back over to our generous host, Tip.
Thank you. Before we close out, please click the survey in the resources section as your input is invaluable to us. I have also pasted the link in the sticky note there at the top of your chat. Your feedback does go a long ways here, so please do let us know about that or any other closing or final thoughts that you've got. Once again, you will receive an email in your inbox shortly after we conclude today's session with a link to view it. I would like to thank Andre, Shivam, and Dylan for an insightful webinar and taking the time to join us today. It's been a pleasure having you all. Thanks for joining this TechStrong learning experience, everyone. Looking forward to seeing you all again. Have a great day.
Thank you, everyone.
Thanks, everyone. Appreciate it.
Thanks all.